Hi folks, in this video we're going to have a look at a question involving the refractive index. So light of a wavelength of 600 nanometers in air falls incident on a glass block of refractive index 1.50. The light is refracted. Part A of the question is asking us to calculate the wavelength, the frequency and the speed of the light in the glass. So first thing we'll do is just draw a quick sketch just to visualise what is happening here. So on the diagram we've shown a ray of light heading towards the air glass boundary. We have the angle of incidence marked out in the air, that's between the incident ray and the normal, and we also have the refracted ray in the glass with the angle of refraction also marked out. The ray of light is being refracted towards the normal once it passes into the glass, and that's because it's moving into a more optically dense medium. At the side I've also listed some of the key bits of information so we can figure out what do we already know and what do we need to find out. So we know that the light has a wavelength of 600 nanometers in air. So in air, I'm going to call that lambda 1 is equal to 600 nanometers, which is 600 by 10 to the minus 9 meters. We do actually know the velocity in air, although it's not actually stated in the question. But that value is a constant and you can find it on your data sheet. It is the speed of light in air, which is 3 by 10 to the power of 8 meters per second. So if we know the velocity and the wavelength in air, then we can work out the frequency in air. Now the reason that that's going to be useful is because we know that the frequency in air will be the same as it is in glass. So we can just use V equals F lambda in order to figure out that frequency. So V is equal to F lambda. If we substitute in our values, we have 3 by 10 to the power of 8 is equal to F multiplied by 600 nanometers, so that's by 10 to the minus 9. So our frequency is 3 by 10 to the 8 divided by 600 by 10 to the minus 9, which is 5 by 10 to the 14 hertz. So the frequency in air is 5 by 10 to the power of 14 hertz. Since the frequency is constant across the two mediums, then the frequency in glass is also 5 by 10 to the 14. So now we need to figure out how are we going to calculate the velocity and how are we going to calculate wavelength, because these are both unknown. So we're not able to use V equals F lambda at this stage. What we can do is use an equation that involves the refractive index, where the refractive index links together the speed of light in air and the speed of light in the medium. In this case, that medium is glass. So our equation here would become 1.50 for the refractive index is equal to the speed of light in air, which is 3 by 10 to the power of 8, divided by the speed of light in the medium, which in this case is glass, and I'm just going to use V to represent that velocity. So rearranging our equation, we have that our velocity is equal to 3 by 10 to the power of 8 divided by 1.50 for the refractive index, which is equal to 2 by 10 to the power of 8 meters per second. So now that we know the velocity in glass, we have 2 by 10 to the power of 8, then the only thing remaining is to work out the wavelength, and we can use V equals F lambda. So V is equal to F lambda, where the velocity is 2 by 10 to the power of 8. That's equal to the frequency, which is 5 by 10 to the power of 14 multiplied by lambda. So lambda is 2 by 10 to the 8 divided by 5 by 10 to the 14, which is 4 by 10 to the minus 7 meters. Or if we wanted to convert that into nanometers, that would be 400 nanometers. So the question asked us to work out the wavelength of the light when it's in the glass, which we found to be 400 nanometers, or 400 by 10 to the minus 9 meters. The frequency in the glass, which we found to be 5 by 10 to the 14 hertz, and then the speed of the light in the glass, which was 2 by 10 to the power of 8 meters per second. For part B of this question, if the angle of refraction in the glass is 30 degrees, calculate the angle of incidence in the air. So this angle R is being given 30 degrees. So here we're going to make use of Snell's law, which is N is equal to sine I over sine R. Now N in this case is the absolute refractive index. We're travelling from air into the medium, which in this case is glass. So our angle of incidence must be in the air, and our angle of refraction will be in the glass. So N is equal to 1.50. That is equal to sine I divided by sine R, which is 30. So we have the sine of 30. If we rearrange that, I'm going to bring the sine 30 over to the left hand side. We have 1.50 multiplied by sine 30 is equal to sine I. Now to work out I, we're going to take the inverse sine of this expression here on the left hand side. So that's the inverse sine of 1.5 times sine 30. So I is equal to sine to the minus 1. That's our inverse sine of 1.50 multiplied by sine 30. You can of course work out that number in the brackets, the 1.5 times sine 30, but when you do, make sure you keep as many decimal places as possible as you carry forward the calculation. So once we pop that into the calculator, we get an answer of 48.59 degrees. So we'll just write that as 48.6 degrees. So that's our angle of incidence. And that would make sense that our angle of incidence is bigger than the angle of refraction.